Okay, this is question page 392, number 35D. I'm excited to work out this one because x equals 4 is a little different. Our axis of revolution is usually either the y-axis or the x-axis. So this one is kind of unique for some of the questions in the book. It's a good idea to take our information and create our own picture. It can help us as a reference tool. So we know square root of x is a boundary. We know that y equals 2 is a boundary. And then we also know that x equals 0, also known as the y-axis, is a boundary. So we have some points where they intersect, and this space in between is our region R. I actually don't want to use R. We'll save that for radius. We also know that our axis of revolution is the vertical line, x equals 4. This is a problem where we need to actually decide, is 4 right here? Is 4 right here? Is 4 right here? So let's find these points early. Let's find these 3 points early. We usually find them at a later step. But to graph our axis, it's a good idea to go ahead and find them now. If we set the square root of x equal to y equals 2, what we get is x equals 4 as a solution. So that lets us know that our vertical line actually belongs right where this point is. So there's our axis of revolution. We're now ready to answer some questions about dx or dy, washer or disk, and outer and inner functions so that we can set up, slice, approximate, and integrate with ease. This is a dy problem. Let me rewrite this. This is a dy problem because this is a vertical line. Any axis of revolution that's a vertical line is going to result in a dy problem. This is also a washer problem because x equals 4 is neither of the 3 boundaries, not a border. Yes, it's true that the line touches the region, but a boundary would be exactly over this line, or exactly over this line, or perhaps exactly over this line. This isn't an actual boundary. It was not written as either of the 3 equations. So it's not a border, it's not a boundary, and this is a washer problem. If dy is our variable, then we need to look at which function is closer horizontally to this axis and which function is farther. For the region in question, it's pretty clear that the square root of x is closer, so we'll give square root of x the label inner. X equals 0 is our function that's farther away from the axis, so we'll give it the label of outer. One thing we want to do is actually take this, and since this is a dy problem, we don't want to think of this as the square root of x. We want to think of this as x equals y squared. That way our function variables are lined up with our integration variables. All right, we know it's dy, we know it's a washer, we see our axis, and we've also identified our inner and outer functions. So we're ready to slice, approximate, and integrate. The area of each section is pi, big R squared minus little r squared. That's our area as a function of big R and little r. To approximate, we're going to use those outer and inner labels. Big R of y is outer minus axis. In this case, the function x equals 2 is farther from our axis of revolution. So 2 is the outer function. I'm so sorry. This isn't the function x equals 2, this is the function x equals 0. X equals 2 actually isn't part of this problem. This is x equals 0, this is our axis. So our outer function is 0. Our inner function, or our axis function is 4, which gives us negative 4 as r of y. This is a little unusual. The result is negative. How can a radius be negative? We'll answer that question in a minute. But suffice to say, outer minus axis is always going to work. Do not worry about this result negative 4. It will be totally fine. We'll discuss that in a moment. Little r of y is the inner function minus the axis. In this case, x equals y squared is much closer to the axis of x equals 4. So we give it that label inner. Minus our axis of 4. No simplification is necessary. So that's our inner function. Now that we know outer and now that we know inner, we can write the area as a function of the variable y. A of y is pi. This is negative 4. Negative 4 is going to be squared. When negative 4 is squared, the negative is irrelevant. In this picture, clearly the big radiuses for every slice have the value of positive 4. They do not have the value of negative 4. However, the negative will be eliminated by the squaring, and our initial problem has disintegrated and is no problem at all. It is probably a good idea to at least simplify this term so that we identify the correct value in here. Technically, this should be a 4, not a negative 4. But when we trust this process and we get a negative value, it will work itself out. So our volume is the integral of pi 16 from this term minus y squared minus 4 squared dy. Our limits of integration, our a and b values, come from the y-axis. It's pretty clear that this is 0. And then if we go back and look at this vertical line, we know that that's the value y equals 2. So that's a key function of y, or a key use, I should say, of y equals 2 in this problem, to let us know where our area stops up and down and give us that b value. So this is our integral expression. In the interest of time, I'm not going to be able to work this one out for you by hand. For the homework, it was perfectly acceptable to evaluate this with a calculator. You just retype this entire expression, but use the letter x. It won't affect what the calculator tells you. At this step, we should declare victory. We should probably draw a picture of a soccer ball. A soccer ball is round and it has several black patches, little triangles. And it also has several white patches, although I believe they're actually hexagons. And now we have a perfect soccer ball. This has been page 392, number 35D.